Hello guys, welcome to my channel. This is the Pandit and you are watching MEP Technical World. In this video we'll learn about basically how to calculate the fault current or short circuit current at primary side of the transformer, which is ST, high tension side. Okay, so before we start the session, I would like to request you, if you are not yet subscribe my channel, please subscribe my channel and also hit the bell icon so you'll get notification regarding my upcoming videos. So let's get started. So basically, what is fault current? So a fault current is an abnormal a fault current is an abnormally high and un, unintended flow of electrical current is in circuit occurring during the fault condition like short circuits. So so basically, what is fault current? It is the abnormal high current. So this is due to the short circuit. Okay, so here as you can see, so this is RYB. So there are three phases over here cable. So this is in normal condition. Load is connected. Now load is getting proper power from through this. Okay, when any fault occurs, means suppose R and Y that's touches to each other, that means at that time what happened between this short circuit happens. So at this condition, high current amount of high current will follow through this circuit, even it will damage the loads and others area, even it causes huge fire as well. So to protect this one, we have to implement circuit breakers, and according to that circuit breaker, even we have to find the fault current or short circuit current actually at this point. What is the actual value, what is the fault current level, what is the current level of this point if any short circuit happens. So according to that only we will select the circuit breakers, actually breaking capacity, and even earth strips. Okay, earthing strips and earthing pits. So here, so what are the causes of fault current? Why basically fault current or short circuit happen in the system? So there are many reasons over here. So we have covered here. So one of main reason is loose connection at terminals. While we are terminating any cables or any towards the machinery or in power systems even, so if there is any loose connection at terminals, okay, then there is a huge chances of getting short circuit and even fall fall huge faults. And another one is overload for long period on live circuits. If you are if we are putting overload, means more than capacity as per designs for long period, then definitely wire will be burned out and it will get to touch to each other, and definitely you get a short circuit, and hence there will be more fault current. Another one is cable insulation failure. Hence this is also due to the insulation, even due to overload. Okay, mechanical damage. So these are the reasons. Due to the insulation failure, again wire touch to each other and it will get short circuit and current will be huge flow. Another one is naked wire carrying electricity collide to each others. So generally when the transmission line, at the side of transmission line, naked wires are, suppose 11 kbs are transmission and distribution through the poles, and if something fall on the cables, then that cables will break and it will collide to each another sides. Even due to sag, it will touch to another cable or wires. So here that condition also short circuit happens. Another one is dust and moisture on the switchgear connection terminal. So due to the dust and moisture, it will also happen. So these are the major reasons due to this only short circuit happens. So now let's calculate the fault current. Okay, so here we have going to here we are going to calculate for the transformer HT side, which is high tensor or primary side. So here we'll take 11 kV from primary side. Okay, so here we have some steps. So to calculate the fault current at HT side, we have to follow these steps. So first we have to select the fault points, okay, where actually fault will happen. Then assume the fault MVA values, okay. Then calculate the short circuit current as per the formula. So this is the formula for short circuit current. So fault MVA divided by square root 3 multiply with kilovolt, which is at fault points. Okay, so you have to follow these three steps to calculate the fault currents. So now let's calculate. So over here I have taken so one transformer. So this, let's say this is 500 kVA transformer, and primary side is 11 kV and secondary side is 415 volts. So this is a step down transformer, distribution transformer, and the power is taking from nearest substation. Okay, so nearest substation. So let's assume the fault is happen at this side, primary side, which is ST side, high tension side, which is what is the level of the fault point, what is the level of the voltage, that is 11 kilo volts, so means 11,000 volt. And suppose here, so I have indicated this is the fault point. Here actually fault happen, let's say short circuit happen at this side, primary side means ST side, 11 kV side. So this is the voltage level at a fault point. Then fault MVA, this is we have assumed 350 MVA. So this is actually capacity of the nearest substation, which uh, we are taking power from there for this transformer. So then we can get the information from that concerned departments. Okay, so here I have assumed fault MVA is 350 MVA. Now let's calculate short circuit current. So to calculate the short circuit current, we know the formula. So fault MVA divided by the square root 3 kV at fault. Let's put the values of fault MVA is 350 MVA. Now let's convert this into kVA. So multiply with 1000 and square root 3 value is 1.732, and fault kV means 11,000, which is this side. Now this 1000 and 1000 will be cut, and this voltage and this voltage. Now remaining is 350 and kilo ampere, and if we multiply 1.732 into 11, then 350 divided by 19.05, if we divided by this one, it will become 18.35 kA. So this is the actually short circuit current or fault current at this point, means high tension side, primary side of this transformer. Now if we know this one fault current, now according to this we'll select the vacuum circuit rate for this transformer protection. We'll use in ST panels. Okay, we have to select the breaking capacity according to this. Suppose here is 18.3 point, so 25 kA will be used the VCB. Okay, as for this. Another one, this value will definitely will help to calculate the earthing strip size and earthing bits. Okay, so this value is most important during the calculation of earthing and even circuit breaker. Okay, circuit breaker uh, breaking capacity selection, which is the unit ka, it's kilo ampere. Okay, so hope you guys understand about basically how to calculate the fault current at HT side. Further video will definitely discuss about how to calculate the earthing strip and earthing fits as per this fault current, and later we'll also calculate the fault current at LT side, means low tension side. Okay, even to calculate the earthings as well. Okay, so thank you so much for watching this video. Please like, share and comment and subscribe, and also hit the bell icon so you'll get notification regarding my upcoming videos. Thank you very much. See you again next video.